So here's something worth thinking about as you settle in tonight. Right now, wherever you are, there's probably a refrigerator humming somewhere nearby. Maybe it's in the next room, maybe it's just down the hall, and it's doing something that would have seemed like actual magic to almost every human being who ever lived. It's making cold. Not finding cold, not harvesting cold from a mountaintop or a frozen lake, but creating it, pulling heat out of the air inside a sealed box and pushing that heat somewhere else. And it does this all day, every day, without you ever really thinking about it. You open the door, your milk is cold, your vegetables are crisp, and you close the door and walk away. But the thing that's happening inside that machine, the physics of it, the engineering of it, the centuries of human ingenuity that went into making it work, that's one of the most fascinating stories in all of technology. And tonight, we're going to walk through it, slowly, from the very beginning. Let's start with something that seems obvious but actually isn't. What is cold? Like, really, what is it? Because for most of human history, people thought of cold as a thing, a substance, something that existed on its own. Hot and cold were opposites, like light and dark, and they were both real, tangible presences. If something was cold, it was because cold had gotten into it. If something was hot, heat had gotten into it. That's intuitive, right? You touch a block of ice, and it feels like cold is flowing into your hand. But here's the thing. That's actually backwards. What's really happening is that heat is flowing out of your hand and into the ice. Cold isn't a substance. Cold isn't a force. Cold is just the absence of heat. It's what's left over when you take heat away. And that distinction, as simple as it sounds, is the entire foundation of refrigeration. Every refrigerator, every air conditioner, every freezer, every cold storage warehouse on the planet works on this one principle. You don't add cold to things, you remove heat from them. You move heat from where you don't want it to somewhere else where you don't mind it being. That's it. That's the whole game. But figuring out how to actually do that, how to reliably move heat in a direction it doesn't naturally want to go, that took centuries. And the story of how we got there is full of strange characters, dead ends, brilliant accidents, and a few ideas so clever they still make engineers smile. But before we get to the machines, let's go way back. Because humans have been trying to keep things cold for thousands of years, long before anyone understood what heat even was. The oldest method is the most obvious one: ice. If you lived somewhere that got cold enough in winter, you could cut blocks of ice from lakes and rivers, drag them to an insulated storage pit, pack them in straw or sawdust, and if you did it right, you'd still have ice come summer. The ancient Mesopotamians were doing this around 1700 BC. They built ice houses, these deep underground chambers with thick walls, and they'd store winter ice in them. The Persians had an even more elegant version. They built structures called yakhchals, and these are genuinely impressive pieces of engineering for the ancient world. Picture a large dome made of mud brick, sometimes 40 or 50 feet tall, with thick walls that could be over 6 feet deep. Below the dome was a deep pit, often with channels that brought in water from mountain aqueducts during winter nights. The desert gets surprisingly cold at night, cold enough to freeze thin layers of water, and the Persians figured out how to use that. They'd let water freeze in shallow pools, then move the ice into the yakhchal before sunrise, where the thick walls and the deep pit and the shape of the dome, which actually created a kind of passive ventilation that pulled warm air up and out, would keep it frozen for months. In the middle of the Iranian desert, in summer heat, that could reach well over 100 degrees. They had ice. They made cold desserts with it. They chilled drinks. This was thousands of years ago. Now, what's interesting about all of these ancient approaches is that none of them are making cold. They're all storing cold, capturing it when nature provides it, and then insulating it as well as they can to slow down the inevitable warming. That's preservation, not generation. And for most of human history, that was the only option. If you didn't live somewhere with cold winters, you just didn't have ice. Tropical civilizations, equatorial regions, cold food storage simply wasn't part of life. And even in places with harsh winters, ice was seasonal. It was labor-intensive to harvest and store, and it melted. Always, eventually, it melted. Fast forward to the early modern period, and you start to see the ice trade. And this is one of those stories that sounds made up, but absolutely isn't. In the early 1800s, a Boston businessman named Frederic Tudor looked at the frozen ponds of New England and saw a business opportunity that everyone else thought was insane. He wanted to cut ice from lakes in Massachusetts, load it onto ships, and sell it in the Caribbean. Havana, Martinique, places where ice was essentially unknown. People laughed at him. His own family thought he'd lost his mind. The idea of shipping ice, a product that was actively trying to destroy itself the entire journey, across the warm Atlantic to tropical ports, seemed like the worst business plan in history. And at first, it kind of was. Tudor's early shipments were disasters. He'd lose huge percentages of his cargo to melting. He couldn't find buyers because nobody in the Caribbean had ice boxes or any way to store the ice once they bought it. He went broke. He went to debtor's prison. But here's what's fascinating about Tudor. He was stubborn in that particular way that sometimes turns out to be genius. He kept experimenting. He figured out that sawdust was an incredible insulator for ice. He developed better packing methods, better ship holds. He started giving away ice for free in tropical ports to create demand, to get people hooked on cold drinks. And then once they couldn't imagine going back to warm lemonade, he started charging. And it worked. By the 1830s and 1840s, Tudor's ice trade was enormously profitable. He was shipping ice from Massachusetts to Calcutta, India, a journey of 4 months across 2 oceans, and he was still delivering ice at the other end. They called him the Ice King. Think about that for a second. In the 1840s, before refrigeration existed, before anyone had built a machine that could make cold, there was a global supply chain for frozen water. Ships full of ice were crossing the planet, and it worked because of insulation, sawdust, hay, careful packing, and because ice has this wonderful property of having a very high latent heat of fusion, which is a fancy way of saying it takes a lot of energy to melt ice. A pound of ice at 32 degrees absorbs about 144 British thermal units of heat before it turns into a pound of water at 32 degrees. That's a lot of heat absorption for not very much temperature change, and it's why ice is such an effective coolant. It soaks up heat like a sponge soaks up water, and it does it at a constant temperature, right at the melting point. Tudor didn't know the physics in those terms, but he understood the practical reality perfectly. The ice trade grew enormous. By the 1880s, the American ice industry was harvesting millions of tons of ice per year from natural sources. New York City alone consumed something like 5 million tons of ice annually. There were ice delivery routes in every city, ice boxes in homes. These were just insulated cabinets with a compartment on top for a block of ice and shelves below for food. And the whole system worked. It was clunky, it was messy, you had to keep buying ice, and in warm weather, the iceman was the most important person on your street. But it worked. And then it started to not work. Because here's the problem with natural ice. It comes from natural water, and by the late 1800s, the lakes and rivers near major cities were getting polluted. Industrial waste, sewage, all manner of unpleasantness was ending up in the same water that people were cutting into blocks and putting in their food storage. There were disease outbreaks linked to contaminated ice. The supply was also unreliable. Warm winters meant less ice, and a bad winter could throw the whole supply chain into chaos. The ice industry was, in a very real sense, running into the limits of depending on nature for something that civilization increasingly couldn't live without. And this is where the story shifts from harvesting cold to making it. Because by the time the natural ice industry was hitting these walls, the science of how to artificially produce cold had actually been understood for quite a while. The engineering just hadn't caught up yet. And to understand how that science developed, we need to talk about something that seems unrelated at first, but is actually at the heart of everything. What happens when liquids evaporate? You've felt this. Everyone has. You step out of a swimming pool on a breezy day and you feel cold, even if the air is warm. Your skin is wet. The water is evaporating, and somehow that makes you cold. Why? Because evaporation requires energy. When a molecule of water on your skin transitions from liquid to gas, it needs to absorb heat to make that transition. It pulls that heat from the nearest available source, which is your skin. So your skin gets cooler. The water molecule carries that heat away with it as it floats off into the air. This is called the latent heat of vaporization. And it's the same basic concept as the latent heat of fusion we talked about with melting ice, just in reverse. Instead of solid to liquid, it's liquid to gas. Now here's what's really clever about this. Different substances evaporate at different temperatures. Water boils at 212 degrees Fahrenheit at normal atmospheric pressure. But other substances, ether, for example, or ammonia or various chemical compounds, boil at much lower temperatures. Ether boils at around 94 degrees Fahrenheit. That means at room temperature, ether is already eager to evaporate, and when it does, it absorbs a significant amount of heat from its surroundings. You can make things genuinely cold just by letting ether evaporate near them. People noticed this surprisingly early. In the 1720s, a Scottish physician named William Cullen conducted what might be the first real demonstration of artificial refrigeration. He used a pump to create a partial vacuum over a container of diethyl ether. By lowering the pressure, he lowered the boiling point of the ether even further, which made it evaporate rapidly, and the rapid evaporation absorbed so much heat that a small amount of water in an adjacent container actually froze. He made ice. In a laboratory in Edinburgh in the 1720s, without any ice to start with, William Cullen made ice by evaporating ether. It was a tiny amount, and the apparatus was completely impractical, and he didn't pursue it as anything more than a scientific demonstration, but the principle was there. The seed of every refrigerator that would ever exist was planted in that moment. And yet, more than a century would pass before anyone turned that principle into a working, practical machine. That gap between understanding the science and building the technology is one of the most interesting things about the history of refrigeration. Because it wasn't that people didn't try. They did. The problem was that building a machine that could reliably evaporate a fluid, capture the heat it absorbed, and then somehow recondense that fluid so you could use it again, over and over in a continuous cycle, that required materials, manufacturing precision, and engineering knowledge that simply didn't exist yet in the 1720s. You needed metal vessels that could hold pressure without leaking. You needed pumps that could run reliably for hours. You needed a deeper understanding of thermodynamics than anyone had at the time. But the idea was out there, floating around in the minds of natural philosophers and tinkerers and physicians, and over the next 100 years, piece by piece, the understanding deepened. And one of the most important pieces of that puzzle came from a man who wasn't thinking about refrigeration at all. He was thinking about steam engines and about what heat actually is, and his name was Sadi Carnot. He was French, he was young, and the slim little book he published in 1824 would eventually reshape how we understand every heat engine and every refrigeration system ever built. But in his own lifetime, almost nobody noticed. Almost nobody read it. Almost nobody cited it. And Carnot himself died just 8 years later, in 1832, during a cholera epidemic in Paris. He was only 36 years old. Most of his papers were burned after his death, as was common practice during cholera outbreaks to prevent the spread of disease. So here's this young man, brilliant, deeply thoughtful, and he writes what will eventually be recognized as one of the founding documents of thermodynamics. And then he's just gone, and the world barely blinks. But let's talk about what he actually figured out, because it matters enormously for understanding how refrigeration works. Carnot was obsessed with a very practical question. France had lost the Napoleonic Wars, and one of the things that haunted French engineers and military thinkers was that Britain had better steam engines. British industry was pulling ahead, and steam power was a big part of why. So Carnot wanted to understand, at the deepest possible level, what determines how efficient a heat engine can be. Not any particular steam engine, but heat engines in general. What's the theoretical limit? Is there a ceiling on how much useful work you can extract from a given amount of heat? And what he realized, and this is the part that connects directly to your refrigerator humming away in the kitchen right now, is that the efficiency of any heat engine depends on the temperature difference between its hot source and its cold sink. The bigger the difference, the more work you can extract. But here's the really profound part. He showed that no engine, no matter how perfectly built, can ever convert all of the heat into work. There's always waste heat that has to be dumped somewhere cooler. Always. It's not an engineering limitation you can clever your way around. It's a fundamental law of nature. Now, Carnot described all of this in terms of an idealized engine, what we now call a Carnot engine, that operates in a perfect, reversible cycle. And here's where it connects to refrigeration in the most beautiful way. If you run a Carnot engine forward, heat flows from hot to cold, and you get work out. But if you run it backward, if you put work in, you can force heat to flow from cold to hot. That's a refrigerator. That's literally the definition of what a refrigerator does. It's a heat engine running in reverse. You're spending energy, doing work, to move heat from a place you want to keep cold to a place where you don't mind it being warm. Think about what that means for a second. The back of your refrigerator is warm. You've probably felt it if you've ever reached behind there. That warmth isn't some unfortunate side effect. That is the whole point. That's the heat that was inside the fridge. The heat that was sneaking in through the door seals and through the walls every time you opened it, being physically pumped out and dumped into your kitchen. Your refrigerator is a heat pump. It's grabbing thermal energy from the cold interior and shoving it out the back into the warmer room. And it takes work to do that, which is why the compressor needs electricity. Carnot didn't live to see any of this applied, and as I said, his work was largely ignored during his lifetime. It took another French engineer, Émile Clapeyron, to rediscover and reformalize Carnot's ideas in 1834, and then later, in the 1850s, Rudolf Clausius in Germany and William Thomson, Lord Kelvin, in Britain independently built on Carnot's foundation to establish what we now call the second law of thermodynamics. That's the one that says heat doesn't spontaneously flow from cold to hot. It always flows from hot to cold unless you do work to force it the other way. Which, again, is exactly what a refrigerator does. It's a machine built to defy the natural direction of heat flow, not by breaking the law, but by paying the energy cost the law demands. So the theoretical understanding was deepening through the early and middle 1800s. But remember, understanding the theory and building a working machine are two very different things. And the people who actually built the first practical refrigeration machines weren't always the ones reading the thermodynamics papers. Sometimes they were doctors or brewers or entrepreneurs in hot climates who just desperately needed a way to make things cold. One of the earliest and most important figures in this practical story is Jacob Perkins. He was an American inventor living in London, and in 1834, the same year Clapeyron was republishing Carnot's work, Perkins filed a patent for what is generally considered the first vapor compression refrigeration system. And this is the direct ancestor of the machine in your kitchen right now. The basic idea goes like this. You take a volatile fluid. Perkins used ether, just like Cullen had, and you let it evaporate inside a closed system of pipes. When it evaporates, it absorbs heat from its surroundings, making those surroundings colder. That's your cooling effect. But then, instead of just letting the vapor drift away like Cullen did, you use a mechanical compressor, a pump, to squeeze that vapor back into a liquid. When you compress the vapor, it gets hot, and you can dump that heat somewhere else, outside the space you're trying to cool. Then the liquid flows back to the evaporator, and the cycle starts again. Evaporate, absorb heat, compress, release heat, repeat. Over and over and over. That cycle. Evaporation, compression, condensation, expansion is the vapor compression cycle, and it is, to this day, the fundamental operating principle of the vast majority of refrigerators, air conditioners, and heat pumps on Earth. Perkins patented it. He built a prototype. And then, honestly, not much happened with it commercially. The machine worked, in the sense that it demonstrated the principle, but it was leaky, it was unreliable, ether was flammable and dangerous, and there wasn't yet a big enough market demand to push through all those engineering problems. The natural ice trade was still booming. Frederic Tudor's ice ships were still sailing. Why would you invest in a complicated, expensive, failure-prone machine when you could just buy a block of ice cut from a frozen lake? But the need was growing, especially in places far from natural ice. And this is where the story shifts to some unexpected locations. One of the most important early chapters in practical refrigeration didn't happen in London or Paris or Boston. It happened in Australia. In the 1850s, a Scottish-born journalist and businessman named James Harrison, who had emigrated to Australia, became fascinated with the cooling effect of ether evaporation. There's a story, and the details are a bit hazy, so take this with a grain of salt, that Harrison first noticed the cooling effect while cleaning type with ether at a printing press. The ether would evaporate off the metal type and leave it startlingly cold. Whether or not that's exactly how it happened, Harrison threw himself into the problem of mechanical refrigeration with real intensity. By 1856, he had built a practical ether vapor compression machine and was granted a patent for it. He installed refrigeration systems in breweries around Victoria, Australia, where keeping beer cold during the brutal summers was a genuine commercial problem worth solving. And here's where you can see the pattern that drives so much engineering innovation. It's not always the grand theoretical insight that moves things forward. Sometimes it's beer. Sometimes it's a brewer in Melbourne saying, "I will pay good money for a machine that keeps my fermentation vats at the right temperature." And that economic pull is what gets the machine built, refined, and made reliable enough to actually use day after day. Harrison's machines worked. They weren't elegant. They required constant maintenance, and ether was still a dangerous working fluid. But they worked. He even attempted, in the 1870s, to ship frozen meat from Australia to England using his refrigeration technology. The first attempt was a disaster. The equipment failed during the voyage and the entire cargo spoiled. It was a financial catastrophe for Harrison personally, but the idea wouldn't die because the economic incentive was just too enormous. Australia and New Zealand and Argentina had vast quantities of cheap meat, and Britain had vast numbers of hungry people willing to pay for it. If you could keep meat frozen on a ship for the weeks-long voyage, you'd unlock an entirely new global trade. And in 1880, the SS Strathlevin successfully carried a cargo of frozen meat from Australia to London using a refrigeration system based on a different technology, a cold air machine rather than vapor compression. The meat arrived in good condition, it sold, and the frozen meat trade was born. Just 2 years later, in 1882, the sailing ship Dunedin carried frozen lamb and mutton from New Zealand to England, and again it arrived successfully. These voyages changed the economies of entire nations. New Zealand's sheep farming industry exploded. Argentina became a major beef exporter, and all of it depended on keeping the hold of a ship cold for weeks on end while crossing the equator. Now, I mentioned that the Strathlevin used a cold air machine rather than vapor compression, and this is worth pausing on because in the second half of the 1800s, there were actually several competing approaches to mechanical refrigeration, and it wasn't at all obvious which one would win. The vapor compression cycle that Perkins and Harrison championed was one approach, but there was also the air cycle machine, sometimes called the Bell-Coleman machine, after its developers, which worked by compressing air, cooling it, and then letting it expand rapidly. When air expands, it cools down. You've felt this if you've ever let air rush out of a tire and noticed the valve getting cold. These air cycle machines had the advantage of using plain air as the working fluid, which meant no toxic or flammable chemicals. But they were bulky, less efficient, and couldn't reach temperatures as low as vapor compression systems. And then there was a third approach, one that would prove enormously important, and it came from a French engineer named Ferdinand Carré. In 1859, Carré patented an absorption refrigeration system, and this worked on a fundamentally different principle than vapor compression. Instead of using a mechanical compressor to squeeze the refrigerant vapor back into a liquid, an absorption system uses heat and a chemical trick. Carré's system used water and ammonia. The ammonia would evaporate and produce the cooling effect, just like in a vapor compression system. But then, instead of being mechanically compressed, the ammonia vapor would be absorbed into water. Ammonia dissolves very readily in water, and then that ammonia water solution would be heated, which would drive the ammonia back out as a high-pressure vapor, ready to be condensed and cycled through again. The brilliant thing about this is that you're replacing the compressor, which is the most mechanically complex and failure-prone part of the system, with a simple heat source. You could run an absorption refrigerator on a gas flame, or waste heat from an industrial process, or even sunlight if you concentrated it enough. And that mattered enormously in the 19th century because reliable mechanical compressors were expensive. They broke down, and they needed a source of mechanical power, a steam engine, or, later, an electric motor. Absorption systems needed none of that. You just needed fire. Think about what that meant in practical terms. If you were running a plantation in the American South in the 1860s, or operating a remote outpost somewhere in colonial India, you might not have access to a skilled mechanic who could maintain a complicated compressor. But you almost certainly had access to fuel you could burn. Carré's absorption machines found a natural home in exactly these kinds of settings. During the American Civil War, in fact, Carré's systems were used in the Confederacy, where the Union naval blockade had cut off the supply of natural ice from the north. Suddenly, southern cities that had depended on ice shipments from New England lakes couldn't get any. And Ferdinand Carré's brother, Edmond Carré, had actually developed a simpler version of the absorption system even earlier. But it was Ferdinand's ammonia water design that proved robust enough for real industrial use. Confederate hospitals and some wealthy households used these French-designed machines to produce ice during the war, which is a fascinating little intersection of engineering, geopolitics, and desperation. But here's the thing about absorption systems. They had their own drawbacks. They were generally less efficient than vapor compression systems when you measured them purely on cooling output per unit of energy input. The coefficient of performance, which is the ratio of how much cooling you get versus how much energy you put in, was typically lower for absorption machines. They also tended to be large. And while they avoided the mechanical complexity of a compressor, they introduced chemical complexity. You had to manage the ammonia water solution carefully, deal with corrosion, handle the fact that ammonia is toxic and has that sharp, eye-watering smell. So it wasn't a clear-cut winner. Each of the three approaches, vapor compression, air cycle, and absorption, had situations where it made the most sense. And this is where the story gets really interesting, because the late 19th century becomes this period of intense competition and experimentation, where engineers and entrepreneurs in different countries are trying to figure out which system works best for which application. It's not a tidy narrative where one technology triumphs immediately. It's messy, it's regional, it's driven by local conditions and available resources, and honestly, by the personalities of the people involved. Let's talk about one of the most consequential applications: brewing. If you had to pick a single industry that drove the development of mechanical refrigeration more than any other in the second half of the 1800s, it would be beer. And that might sound funny, but think about it. Lager beer, the kind that became enormously popular in Europe and America during this period, requires cold fermentation. Unlike ales, which ferment at warmer temperatures, lager yeast works best at around 45 to 55 degrees Fahrenheit. Traditionally, brewers in Bavaria and Bohemia had brewed lager in winter and stored it in cold cellars packed with ice, harvested from frozen lakes and rivers. The word lager itself comes from the German word lagern, meaning to store. These brewers were completely dependent on natural cold. But as lager's popularity exploded, driven partly by waves of German immigration to the United States, breweries needed to produce it year-round, and they needed to produce a lot of it. You couldn't just wait for winter. You couldn't rely on the natural ice supply, which was variable and, in warmer climates, simply unavailable. Breweries became the first major industrial customers for mechanical refrigeration, and they were willing to pay for it because the alternative was shutting down production for months of the year. Carl von Linde is the name you need to know here. He was a German engineer, a professor at the Technical University of Munich, and he approached the problem of refrigeration with a rigor that was, frankly, ahead of his time. In the early 1870s, Linde published a series of papers analyzing refrigeration systems from a thermodynamic perspective, really applying the theoretical framework that Carnot and Clausius had developed to the practical problem of building better cooling machines. He wasn't just tinkering, he was calculating. He looked at the existing machines, identified where they were losing efficiency, and designed improved vapor compression systems that used ammonia as the refrigerant. Now, ammonia is a remarkable refrigerant in many ways. It has excellent thermodynamic properties, a high latent heat of vaporization, meaning it absorbs a lot of heat when it evaporates, which is exactly what you want. It's also relatively cheap and was widely available. The downside, of course, is that ammonia is toxic and has that intensely pungent smell. A leak in an ammonia system is not something you can ignore. But for industrial applications, where the machinery was housed in a separate room or building, away from the public, ammonia worked beautifully. And Linde's machines were good. Really good. He founded a company in 1879, the Gesellschaft für Linde's Eismaschinen, which translates roughly to the Linde Ice Machine Company. And within a few years, his systems were being installed in breweries across Germany, across Europe, and eventually around the world. By the mid-1880s, Linde had sold more than 700 refrigeration units. That's an astonishing number for what was still a relatively new technology. And the impact on brewing was transformative. Breweries could now maintain precise temperature control during fermentation and storage, regardless of the season or the local climate. This didn't just make year-round production possible, it made the product more consistent. Before mechanical refrigeration, every batch of lager was at the mercy of weather fluctuations. A warm spell during fermentation could ruin an entire batch. Now, the brewer controlled the temperature. The beer tasted the same in July as it did in January. And that consistency, that reliability, is something we take completely for granted today. But it was revolutionary. Here's the kicker, though. Linde's success wasn't just about building good machines. It was about understanding the science deeply enough to optimize them. He knew, from Carnot's principles, that the efficiency of his refrigeration cycle depended on minimizing the temperature differences across which heat was being transferred, on reducing friction losses in the compressor, on choosing a refrigerant with the right thermodynamic properties. He was one of the first engineers to truly bridge the gap between theoretical thermodynamics and practical machine design in the field of refrigeration. And his work had ripple effects far beyond beer. The same technology that kept fermentation tanks cold could keep meat cold, could keep dairy cold, could eventually keep your living room cold. But let's stay with the 1880s for a moment, because something else was happening that would reshape the refrigeration landscape entirely. The natural ice industry was starting to collapse. Remember Frederic Tudor and his ice trade? By the 1880s, the natural ice business in the United States was enormous. Millions of tons of ice harvested from lakes and rivers every year, shipped by rail and wagon to cities across the country. But the industry had a problem, and it was getting worse. The same rivers and lakes that supplied ice were increasingly polluted by industrial waste and sewage. Cities were growing rapidly, and their waste was flowing into the same waterways that ice harvesters depended on. There were growing public health concerns about the safety of natural ice. Typhoid, cholera, diseases linked to contaminated water, could potentially be transmitted through ice cut from polluted sources. The medical understanding of germ theory was advancing rapidly in this period, thanks to the work of Pasteur and Koch, and people were starting to make the connection between dirty water, dirty ice, and disease. This created a powerful incentive to switch to manufactured ice made from clean distilled water using mechanical refrigeration. And it created a market opportunity that entrepreneurs were eager to exploit. Ice-making plants began springing up across the American South and in other warm climates, where natural ice had always been expensive to import. By the 1890s, manufactured ice was overtaking natural ice in many markets. The transition wasn't instant. Natural ice harvesting continued into the early 20th century in some regions, but the writing was on the wall. Mechanical refrigeration wasn't just a novelty or an industrial tool anymore. It was becoming a public health necessity. And this brings us to a broader point about how refrigeration changed the world in ways that go far beyond keeping things cold. Think about cities. Before refrigeration, the food supply of a city was fundamentally constrained by geography and season. You ate what could be grown nearby and what could be preserved through salting, smoking, pickling, or drying. Fresh meat, fresh milk, fresh produce. These were luxuries that depended on proximity to farms and on the weather cooperating. Refrigeration broke those constraints. It made it possible to transport perishable food over long distances and store it for extended periods. And that, in turn, made it possible for cities to grow much larger than they ever could have before. The megacities of the 20th century, places with millions of people living far from any farmland, are only possible because of refrigeration. It's one of those invisible infrastructures, like sewage systems or electrical grids, that we never think about, but that literally make modern urban life viable. Now, while Linde was dominating the European market and the ice industry was transforming in America, engineers were also pushing refrigeration technology in another direction, toward ever lower temperatures. And this is where the story takes a turn toward pure science, because the quest for extreme cold would lead to some of the most remarkable discoveries in physics. Linde himself would play a central role in this. In the 1890s, he turned his attention to the liquefaction of gases, taking gases like oxygen, nitrogen, and eventually air itself, and cooling them to the point where they became liquid. This required reaching temperatures far below anything needed for food preservation or brewing. We're talking about temperatures below -300 degrees Fahrenheit, approaching what scientists call absolute zero, the theoretical lowest possible temperature where all thermal motion ceases. The race to liquefy gases had been going on for decades. Michael Faraday had liquefied chlorine and several other gases back in the 1820s and 1830s by combining pressure and cooling. But some gases, oxygen, nitrogen, hydrogen, stubbornly refused to liquefy no matter how much pressure was applied at room temperature. These were called permanent gases. And for a while, some scientists believed they truly couldn't be liquefied. The breakthrough came when researchers realized that these gases had what's called a critical temperature, a temperature above which no amount of pressure will turn them into a liquid. You had to cool them below their critical temperature first, and then apply pressure. For oxygen, that critical temperature is about -181 degrees Fahrenheit. For nitrogen, it's even lower. For hydrogen, lower still. In 1877, two scientists, Louis-Paul Cailletet in France and Raoul Pictet in Switzerland, independently managed to produce small amounts of liquid oxygen, though in fleeting misty droplets rather than in bulk. It was a proof of concept, a glimpse of what was possible. But producing liquid gases in useful quantities required a different approach, And this is where Linde's engineering brilliance came back into play. In 1895, he developed a process for liquefying air on an industrial scale, using a technique called regenerative cooling. The idea is elegant. You compress air, let it cool, then allow it to expand through a narrow valve. When a gas expands without doing external work, what physicists call a Joule-Thomson expansion, it cools down, at least for most gases, at reasonable temperatures. You take that slightly cooled expanded air and use it to pre-cool the next batch of compressed air before it expands. Each cycle gets a little colder, and a little colder, and a little colder, until eventually the air gets cold enough to liquefy. It actually turns into a liquid, right there in the apparatus. Drip by drip, pooling at the bottom of the device like the most hard-won substance on Earth. And once you have liquid air, you can do something remarkable with it. You can separate it into its component gases. Because air isn't just one thing, right? It's a mixture. About 78% nitrogen, 21% oxygen, and then small amounts of argon, carbon dioxide, neon, and a handful of other trace gases. And each of those components has a slightly different boiling point. Nitrogen boils at about minus 320 degrees Fahrenheit. Oxygen boils a bit warmer, around minus 297. So if you take liquid air and carefully let it warm up, the nitrogen boils off first, leaving behind liquid that's increasingly rich in oxygen. This process, fractional distillation of liquid air, became the foundation of an entire industry. Suddenly, you could produce pure oxygen, pure nitrogen, pure argon, in bulk, reliably, affordably. And that changed everything from steelmaking to medicine to welding to rocketry, all flowing downstream from refrigeration technology. Linde patented his air liquefaction process and built a company around it that still exists today, in a sense. Linde plc remains one of the largest industrial gas companies in the world. Think about that lineage, from a professor trying to help Munich brewers keep their lager cold, to a global enterprise supplying gases that make modern industry possible. It's one of those through lines in engineering history that's almost too clean, too perfect, but it's real. The science of making things cold turned out to be inseparable from the science of understanding what matter actually is, how gases behave, what happens at the extremes of temperature and pressure. But let's come back down from those cryogenic heights for a moment, because while Linde was pushing toward absolute zero, something much more immediate was happening in everyday life. Refrigeration was leaving the factory and the brewery and the ice plant, and it was starting to enter people's homes. And this transition, from industrial technology to household appliance, is one of the most consequential shifts in the entire story. It changed what people ate, where they lived, how cities were designed, what jobs existed. It's arguably as transformative as electrification itself. And like most transformations, it didn't happen overnight. It took decades, and it involved some genuinely strange detours along the way. In the late 1800s and early 1900s, most American households still relied on iceboxes, insulated wooden cabinets where you'd place a block of ice, usually delivered by an iceman who came around with a horse-drawn wagon. The ice would slowly melt over the course of a few days, keeping the food inside cool enough to slow spoilage. It worked, more or less, but it was messy, inconsistent, and expensive over time. The ice dripped, the drip pan overflowed if you forgot to empty it. The food nearest the ice got too cold, while the food farther away wasn't cold enough, and you were always at the mercy of the delivery schedule. If the iceman didn't come, or if a heat wave hit and your block melted faster than expected, you were out of luck. So there was a clear market for a mechanical refrigerator that could sit in your kitchen and make its own cold. The technology existed. Vapor compression had been proven for decades at industrial scale. The challenge was miniaturizing it, making it safe, making it affordable, and making it quiet enough that you'd actually want it humming away in your home. The first serious attempt at a household refrigerator is generally credited to Fred Wolf, who in 1913 introduced a unit called the ASHRAE, short for Domestic Electric Refrigerator. It was essentially a small compressor unit that sat on top of an existing icebox. It was crude, expensive, and not particularly reliable. Around the same time, a few other inventors were tinkering with similar ideas, but the machine that really kicked off the home refrigerator market was the Kelvinator, introduced in 1918 by Nathaniel Wales and Edmund Copeland. And then, in 1919, a company called Frigidaire, originally the Guardian Refrigerator Company, was purchased by General Motors, of all things. William Durant, who founded GM, saw refrigerators as the next big consumer product, the same way automobiles had been. And he wasn't wrong. But here's the thing. Those early home refrigerators were genuinely problematic. They used the same refrigerants that industrial systems used: ammonia, sulfur dioxide, methyl chloride. And these chemicals are not things you want leaking in your kitchen. Ammonia is toxic and has that unmistakable sharp smell. Sulfur dioxide is corrosive and poisonous. Methyl chloride is both toxic and flammable. And leak they did, because the seals and compressors of the 1920s were nowhere near as reliable as what we have today. There were incidents, people got sick. In 1929, a methyl chloride leak at a Cleveland hospital killed more than 100 people. Though the exact circumstances and death toll are debated by historians, the incident was real and it was devastating. It underscored a genuine public safety crisis. Refrigeration was incredibly useful, but the chemicals that made it work could kill you. This is the problem that led to one of the most consequential and ultimately tragic inventions in the history of chemistry. And it starts with a man named Thomas Migley Jr. Now, Migley is a fascinating and deeply complicated figure. He was a mechanical engineer by training, working for General Motors in the 1920s, and he had a genuine gift for applied chemistry, for finding practical solutions to industrial problems. His first big success was discovering that adding tetraethyl lead to gasoline eliminated engine knock, the pinging sound that happened when fuel ignited unevenly in a cylinder. Leaded gasoline worked beautifully from an engineering standpoint. It made engines run smoother, more efficiently, more powerfully. It was also, as we now know, an environmental and public health catastrophe that poisoned millions of people over decades. But that's a different story, though it's worth noting, because it establishes a pattern with Migley: brilliant short-term solutions with devastating long-term consequences. In the late 1920s, Frigidaire, still owned by General Motors, asked Migley and his team to find a new refrigerant, something that was non-toxic, non-flammable, stable, and that had the right thermodynamic properties to work efficiently in a vapor compression cycle. That's a tall order, if you think about it. You need a substance that boils at the right temperature, absorbs a lot of heat when it evaporates, is easy to compress back into a liquid, doesn't corrode the machinery, doesn't react with lubricating oils, doesn't break down over time, won't poison anyone if it leaks, and won't catch fire. Finding a single substance that checks all those boxes is genuinely difficult. Migley approached it systematically, studying the periodic table and focusing on compounds involving fluorine, which tends to form very stable, non-toxic bonds. within just 3 days, and this speed is almost legendary in chemistry circles. He and his colleagues identified dichlorodifluoromethane as a promising candidate. It's a molecule with 1 carbon atom, 2 chlorine atoms, and 2 fluorine atoms. They called it Freon 12, and it was, by every measure that mattered at the time, a miracle substance. Non-toxic, you could breathe it without harm. Non-flammable, you could hold a match to it and nothing happened. Chemically stable, it didn't corrode metals or break down in the system. And it had nearly perfect thermodynamic properties for refrigeration. It boiled at about -22 degrees Fahrenheit at atmospheric pressure, which meant it could absorb heat from a refrigerator's interior and then be easily compressed and condensed back to a liquid by a modest compressor. In a famous demonstration in 1930, Migley stood before the American Chemical Society, inhaled a lungful of Freon, and then used it to blow out a candle. In one theatrical breath, he proved it was both non-toxic and non-flammable. The audience was impressed. The industry was transformed. Freon and its chemical cousins, collectively called chlorofluorocarbons, or CFCs, rapidly replaced ammonia, sulfur dioxide, and methyl chloride in virtually all refrigeration and air conditioning systems. They were also adopted as propellants in aerosol cans, as blowing agents for foam insulation, and as solvents for cleaning electronics. By the mid-20th century, CFCs were everywhere, and they were considered one of the great success stories of industrial chemistry. And for decades, that assessment seemed entirely justified. Home refrigerators became safe, affordable, and ubiquitous. By 1944, about 85% of American homes had a mechanical refrigerator. The icebox was dead, the iceman was out of a job, and the way people ate changed fundamentally. You could buy fresh meat, milk, vegetables, and keep them for days without spoilage. You could store leftovers. You could make ice whenever you wanted. Frozen food became a viable industry. Clarence Birdseye had figured out flash freezing techniques in the 1920s, but it was widespread home refrigeration that made frozen food a mass-market reality. Think about what that means for daily life. Before refrigeration, shopping for food was essentially a daily task. You bought what you needed for that day, maybe the next day, because anything perishable wouldn't last longer than that. Refrigeration compressed the frequency of shopping, expanded the variety of food available, reduced waste in some ways, though it created new forms of waste in others, and fundamentally altered the rhythm of domestic life. It also enabled the rise of the supermarket, because now people could buy in bulk and store things at home. The entire supply chain of food, from farm to processing plant to truck to store to your kitchen, became dependent on an unbroken chain of refrigeration. We call it the cold chain, and it's one of the most critical pieces of infrastructure in the modern world, even though most people never think about it. And air conditioning, which is really just refrigeration applied to indoor spaces rather than to a food compartment, was transformed by CFCs too. Willis Carrier had built the first modern air conditioning system in 1902, originally to control humidity in a printing plant in Brooklyn. But early air conditioning systems used the same problematic refrigerants as early refrigerators. CFCs made air conditioning safe and practical for homes, offices, movie theaters, hospitals, and eventually cars. Air conditioning made the American Sun Belt habitable in a way it hadn't been before. The massive population growth of cities like Houston, Phoenix, Atlanta, Las Vegas. That doesn't happen without air conditioning. The political map of the United States was reshaped by refrigeration chemistry. So Thomas Midgley's invention seemed like an unqualified triumph. He received awards, accolades, was elected to the National Academy of Sciences. He had no idea, nobody did, that the very stability that made CFCs so safe in your kitchen made them extraordinarily dangerous in the atmosphere. Because those molecules were so stable, so resistant to breaking down, that when they eventually leaked out of refrigerators and air conditioners and aerosol cans and drifted up into the stratosphere, they just stayed there, intact, for decades, until they reached the ozone layer, about 15 to 35 kilometers above the Earth's surface, where intense ultraviolet radiation finally had enough energy to break them apart. And when those CFC molecules broke apart, they released free chlorine atoms. And a single chlorine atom, once liberated in the stratosphere, can destroy tens of thousands of ozone molecules before it's finally neutralized. Tens of thousands. That's not a typo. One single chlorine atom acts as a catalyst. It doesn't get used up in the reaction. It breaks apart an ozone molecule, steals one oxygen atom to form chlorine monoxide, and then that chlorine monoxide bumps into a free oxygen atom, releases the chlorine, and the whole cycle starts again. Over and over and over. A single chlorine atom can persist in the stratosphere for something like 2 years, just chewing through ozone molecules the entire time. And every CFC molecule that drifts up there releases not just one, but multiple chlorine atoms. Freon 12, the one Migley invented, has 2 chlorine atoms per molecule. Other CFCs have 3, so you start to see the scale of the problem. Now, here's the thing about ozone. The ozone layer isn't very thick to begin with. If you could somehow gather up all the ozone in the entire atmosphere and compress it down to sea level pressure, it would form a layer only about 3 millimeters thick. 3 millimeters. That's it. That's all that stands between you and the full intensity of the sun's ultraviolet C and most of its ultraviolet B radiation, the wavelengths that cause skin cancer, cataracts, damage to phytoplankton, disruption of entire ecosystems. And we were eating through it with chlorine atoms released from the very molecules we'd celebrated as miracles of safety. The story of how we figured this out is one of the most important scientific detective stories of the 20th century, and it starts with a guy named Mario Molina and his colleague Frank Sherwood Rowland at the University of California, Irvine. In 1974, Molina and Rowland published a paper in the journal Nature that laid out the chemistry I just described, the mechanism by which CFCs could deplete stratospheric ozone. And their paper was not warmly received by everyone. The CFC industry was enormous by then. Billions of dollars. DuPont alone was producing a huge share of the world's CFCs. And here were 2 chemists saying essentially that this entire class of wonder chemicals was slowly destroying the planet's UV shield. The pushback was fierce. Industry groups questioned the science, funded counter-research, argued that the amounts were too small to matter, that natural processes would compensate. Sound familiar? It should. It's a pattern we've seen before and since. But Molina and Rowland were careful, methodical scientists, and their chemistry held up. Other researchers confirmed and extended their findings. The scientific consensus built steadily through the late 1970s. The United States actually banned CFCs in aerosol spray cans in 1978. Spray cans, not refrigerators or air conditioners, just the aerosol propellant use. A few other countries followed. But the bigger uses continued, and global CFC production, after a brief dip, started climbing again in the early 1980s. And then came the shock. In 1985, a team of British Antarctic Survey scientists, Joe Farman, Brian Gardner, and Jonathan Shanklin, published a paper showing that springtime ozone levels over Antarctica had dropped dramatically, not by a few percent, by roughly 40% compared to 1960s levels. A massive, gaping thinning of the ozone layer right over the South Pole, appearing every Antarctic spring, the ozone hole, as the media quickly named it. Here's what's remarkable about this discovery. NASA had satellites measuring ozone from space. The total ozone mapping spectrometer aboard the Nimbus 7 satellite, launched in 1978. The satellite had actually been recording the same decline, but the data processing software had been programmed to flag readings that low as errors and discard them. The computer essentially said, "These numbers can't be right. They're too low. Must be instrument malfunction." So the most sophisticated monitoring system in the world missed what 3 scientists with ground-based instruments in Antarctica caught. When NASA went back and reprocessed the satellite data without the error filter, there it was, a vast, unmistakable hole in the ozone, clearly visible from space, getting worse every year. That image, the satellite view of the ozone hole, rendered in those alarming purples and blues, became one of the most powerful environmental images of the century. It made the abstract chemistry real. People could see it, and it scared them, rightly so. The response, and this is the part that gives you a little bit of hope about humanity's capacity to act on scientific evidence, was remarkably swift by international standards. In 1987, just 2 years after the ozone hole was confirmed, representatives from nations around the world gathered in Montreal and signed what became known as the Montreal Protocol on Substances that Deplete the Ozone Layer. It committed signatory nations to phasing out production and consumption of CFCs and other ozone-depleting substances on a defined timeline. And it worked. It actually worked. Every country in the United Nations eventually ratified it, every single one, making it the first universally ratified treaty in UN history. CFC production plummeted. DuPont, which had initially resisted, pivoted and began developing alternatives. The protocol has been strengthened several times since, accelerating the phase-out schedules and adding new substances to the list. Molina and Rowland, along with the Dutch chemist Paul Crutzen, who had done earlier foundational work on ozone chemistry, shared the Nobel Prize in Chemistry in 1995. And the ozone layer, slowly, is healing. Current projections suggest it should return to 1980 levels sometime around the middle of this century, maybe 2066 for the Antarctic hole specifically. It's a long, slow recovery because those CFC molecules already in the stratosphere last for decades, some for over a century, but the trajectory is in the right direction. So think about what happened here. An engineer, Midgley, solved a real urgent problem. People were dying from toxic refrigerant leaks. He found a molecule that was genuinely safe in every way anyone could test at the time. That molecule transformed daily life for billions of people. And then, decades later, it turned out to have a catastrophic side effect that nobody could have predicted with the science available in 1930. It's not a story of villainy. It's a story of unintended consequences on a planetary scale. And it's a reminder that when you engineer something that's incredibly stable and you release billions of tons of it into an open system like the Earth's atmosphere, the consequences can be profound and surprising. Now, the Montreal Protocol didn't just ban CFCs and leave the refrigeration industry to figure things out on their own. The phase-out was gradual, and it was accompanied by a massive search for replacement refrigerants. And this is where the story gets into the chemistry that's still shaping refrigeration engineering today. The first generation of replacements were HCFCs, hydrochlorofluorocarbons. These still contained chlorine, but they also had hydrogen atoms in the molecule, which made them less stable in the lower atmosphere. They'd break down before most of them reached the stratosphere, so their ozone depletion potential was much lower than CFCs, maybe 2 to 5% as damaging. They were a transitional solution, a bridge. The most common one was HCFC22, also called R22. And if you had a home air conditioning system installed in the 1990s or early 2000s, it probably used R22. But HCFCs were always understood to be temporary. The next generation were HFCs, hydrofluorocarbons, no chlorine at all, zero ozone depletion potential. Problem solved, right? Well, not exactly. Because HFCs turned out to be extraordinarily potent greenhouse gases. Some of them have a global warming potential thousands of times greater than carbon dioxide, molecule for molecule. HFC 134A, which became the standard refrigerant in car air conditioning systems and many commercial refrigeration units, has a global warming potential of about 1,430, meaning 1 kilogram of it traps as much heat over a 100-year period as 1,430 kilograms of CO2. And HFC 410A, widely used in residential heat pumps and air conditioners, is even worse, around 2,088 times CO2. So we solved the ozone problem and walked straight into a climate problem. The sheer quantity of HFCs being produced and inevitably leaked from manufacturing, from servicing, from end-of-life disposal of equipment was becoming a significant contributor to global warming. By some estimates, if HFC use had continued to grow unchecked, it could have added as much as 0.5 degrees Celsius to global warming by the end of this century. 0.5 degrees doesn't sound like much until you remember that the entire Paris Agreement is trying to keep total warming below 1.5 to 2 degrees. This led to the Kigali Amendment to the Montreal Protocol, adopted in 2016, which committed nations to phasing down HFC production by 80% or more over the coming decades. And that brings us to the current frontier of refrigerant chemistry, the search for substances that don't destroy ozone, don't warm the climate, aren't toxic, aren't flammable, have good thermodynamic properties, and are compatible with existing equipment designs. It's a genuinely difficult engineering challenge because those requirements pull in different directions. The reason CFCs were so good as refrigerants was precisely because of their stability and inertness. Take that away, and you're left with trade-offs. The current leading candidates fall into a few categories. There are HFOs, hydrofluorolefins, which are chemically similar to HFCs, but contain a carbon-carbon double bond that makes them much less stable in the atmosphere. They break down in days rather than years, so their global warming potential is very low, often below 10. HFO 1234YF is already the standard refrigerant in new car air conditioning systems in Europe and increasingly in the United States. But HFOs tend to be mildly flammable, which brings us back, in a strange full circle, to the safety concerns that Migley was trying to solve in the first place. Not as dangerous as the old refrigerants. We're talking about a low flammability classification, not the kind of thing that explodes. But it still requires careful engineering of the systems that use them. And then there's the old guard making a comeback. Natural refrigerants, carbon dioxide, ammonia, hydrocarbons like propane and isobutane. These were the very first refrigerants, the ones used before Migley came along, and they're experiencing a renaissance. Ammonia never really went away in industrial refrigeration. Large cold storage warehouses, food processing plants, ice rinks. Because it's thermodynamically excellent and very efficient. It's toxic, yes, but in industrial settings with trained operators and proper safety systems, it's manageable. Carbon dioxide, or R744, is being used in an increasing number of commercial systems, particularly in supermarkets in Europe. It operates at much higher pressures than conventional refrigerants, which requires beefier components, but it has essentially zero direct environmental impact. And hydrocarbons, propane as R290, isobutane as R600A, are already the dominant refrigerants in household refrigerators across Europe and much of Asia. Your refrigerator, if it was made in the last decade or so and sold in Europe, almost certainly runs on isobutane. There's only about 150 grams of it in there, a tiny amount, and modern compressor designs have made the flammability risk negligible for that application. So the refrigerant story is really a story about trade-offs, about how every engineering choice has consequences that ripple outward in ways you can't always foresee, and about how the process of refinement never really ends. You solve one problem, you create another, you solve that one, and something else emerges. It's not failure, it's how engineering actually works in the real world, where perfect solutions don't exist, and the best you can do is keep improving, keep learning, keep adapting. But let's step back from the chemistry for a moment and talk about something equally important, the machinery itself. Because while all this refrigerant drama was playing out, the mechanical heart of the refrigeration system, the compressor, was undergoing its own quiet revolution. And this is one of those stories that doesn't get much attention because it happened gradually, inside sealed metal housings where nobody could see it, but it changed everything about how refrigeration fits into daily life. Because the compressor is the part that does the actual work. It's the thing that takes low-pressure refrigerant vapor and squeezes it into high-pressure, high-temperature vapor so the whole cycle can keep turning. Without it, you just have a bunch of pipes and chemicals sitting there, doing nothing. And the way compressors evolved over the last century or so is one of those beautiful engineering stories, where incremental improvements, each one seemingly small, add up to something transformative. So let's start with the early days. The first refrigeration compressors, the ones in those big industrial machines from the late 1800s, were essentially adapted steam engine technology. They were reciprocating compressors, pistons moving back and forth inside cylinders, drawing in gas on one stroke and compressing it on the next. Same basic idea as a car engine, just running in reverse in a sense. Instead of expanding gas pushing a piston to create motion, you're using motion to push a piston to compress gas. These early machines were enormous. We're talking compressors the size of a room, driven by belts connected to steam engines or electric motors, with exposed crankshafts and flywheels and all kinds of moving parts that needed constant lubrication and maintenance. They leaked. They were loud. They vibrated. They required skilled operators to keep them running. And they worked, but they were absolutely not the kind of thing you could put in someone's kitchen. The first big shift came with the idea of the hermetic compressor, and this is where the story gets really interesting. The concept is beautifully simple in retrospect. Instead of having the motor outside the compressor housing, connected by a shaft that passes through a seal, which is always going to be a potential leak point, you put the motor inside the same sealed housing as the compressor mechanism. You weld the whole thing shut. No shaft seal, no leak path, no belt, no coupling. The motor and compressor become one sealed unit. The refrigerant itself flows over the motor windings, which actually helps cool the motor. It's elegant. Now, getting there wasn't easy. The idea had been floating around since the early 1900s, but making it practical required solving several problems at once. You needed electric motors that could operate reliably while bathed in refrigerant and lubricating oil. You needed materials that wouldn't degrade in that chemical environment. You needed manufacturing precision good enough that you could seal these things up at the factory and have them run for years, eventually decades, without anyone ever opening them up for service. Think about what that means. You're asking someone to build a machine with moving parts, seal it inside a metal shell, and guarantee it'll just keep working. That's an extraordinary level of confidence in your engineering. General Electric was one of the early pioneers here. Their monitor-top refrigerator, introduced in 1927, used a hermetically sealed compressor sitting on top of the cabinet. That's where the name came from. It looked a bit like the turret on the Civil War ironclad ship, the USS Monitor. These were among the first truly reliable home refrigerators, and some of them ran for 40, 50, even 60 years. There are documented cases of monitor tops still running in the 2000s, which is just remarkable when you think about it. Part of that longevity came from the simplicity of the hermetic design. Fewer things that could go wrong, no seals to wear out, no belts to replace. But the real mass-market breakthrough in compressor design came in the 1930s and 1940s, when manufacturers figured out how to make hermetic reciprocating compressors cheaply and reliably enough for true mass production. Companies like Tecumseh, Embraco, and later Danfoss became the giants of this world, pumping out millions of these little sealed units. And they kept getting smaller. The compressor in a modern household refrigerator is roughly the size of a small melon. It weighs maybe 10 or 15 pounds, and it runs so quietly that most people don't even notice it cycling on and off. Compare that to those room-sized monsters from the 1890s, doing essentially the same thermodynamic job, and you get a sense of how far the engineering has come. Here's what's really clever about how a modern reciprocating hermetic compressor works, just so you have the picture. Inside that sealed shell, there's a small electric motor, an induction motor typically, connected to a crankshaft. The crankshaft drives a piston, or sometimes two pistons, back and forth inside a cylinder. On the intake stroke, the piston pulls back and low-pressure refrigerant vapor gets drawn in through a reed valve. That's just a thin flap of spring steel that opens and closes with pressure differences, no moving parts in the traditional sense, incredibly reliable. On the compression stroke, the piston pushes forward, the intake valve closes, the gas gets compressed, and when the pressure gets high enough, another reed valve on the discharge side pops open and the high-pressure gas flows out into the condenser. The whole thing happens maybe 30 to 60 times per second, depending on the motor speed and the power supply frequency. And all of this is happening inside a sealed steel shell, sitting quietly in the back of your kitchen, and you never think about it. But reciprocating compressors, for all their reliability, have some inherent limitations. They vibrate, because you've got a piston slamming back and forth. They have valves that can fatigue and fail. They have a certain minimum size below which they're hard to make efficiently. And their efficiency, while decent, has a ceiling that's hard to push past because of the stop-start nature of the piston motion. There are always losses associated with the gas flow reversing direction, with the dead volume in the cylinder that doesn't get fully swept. And this is where the scroll compressor enters the picture. And honestly, this is one of my favorite pieces of mechanical engineering. The scroll compressor was actually invented way back in 1905 by a French engineer named Léon Creux. He patented it, and the idea is gorgeous. Instead of a piston going back and forth, you have two spiral-shaped scrolls. Imagine two identical spirals, like the kind you'd draw with a compass, but three-dimensional, like a rolled-up ribbon standing on its edge. One scroll is fixed, the other one orbits. It doesn't rotate, it orbits, moving in a small circular path without spinning. And as it orbits, the crescent-shaped pockets of gas between the two spirals get progressively smaller as they move from the outside edge toward the center. Gas enters at the outer edge, gets trapped between the scrolls, and gets squeezed into a smaller and smaller volume as it spirals inward until it reaches the center and gets discharged at high pressure. It's continuous compression. There's no intake stroke and compression stroke. Gas is always being drawn in at the outside and always being compressed toward the middle. Multiple pockets of gas are being compressed simultaneously at different stages. It's smooth, it's quiet, it has very few moving parts, essentially just the orbiting scroll and the motor driving it. No valves, no reciprocating mass, almost no vibration. Léon Creux was ahead of his time because in 1905, nobody could actually manufacture the thing. The spiral surfaces have to mate with extraordinary precision. We're talking tolerances of a few thousandths of an inch. And early 20th century machining just wasn't up to the task. So the scroll compressor sat there as a beautiful idea on paper for decades. It wasn't until the 1970s and 1980s that manufacturing technology, CNC machining, better materials, tighter quality control, finally caught up with Creux's vision. Copeland, which is now part of Emerson, was one of the first companies to commercialize scroll compressors for air conditioning and refrigeration in the mid-1980s. And they took off. Today, scroll compressors dominate the residential and light commercial air conditioning market. If you have a central air conditioning system in your home that was installed in the last 20 years or so, there's a very good chance it uses a scroll compressor. They're more efficient than reciprocating compressors in that size range. They're quieter, they last longer because there are fewer parts to wear out, and they handle liquid slugging better. That's when a bit of liquid refrigerant accidentally makes it into the compressor, which can destroy a reciprocating compressor. But a scroll can usually handle without catastrophic damage. Now for larger systems, big commercial buildings, industrial processes, there's another type that's been quietly dominant for decades, and that's the screw compressor. This one uses two helical rotors that mesh together like gears, trapping gas between the rotors and the housing and compressing it as the gas moves along the length of the rotors. Screw compressors are workhorses. They can handle huge volumes of gas, they're very reliable, and they can operate efficiently across a wide range of conditions. If you've ever been in a large commercial building and heard a low, steady hum coming from the mechanical room, that might well be a screw compressor doing its thing. And then there's the centrifugal compressor, which is a completely different approach. Instead of positive displacement, physically trapping gas and making the space smaller, a centrifugal compressor uses a high-speed impeller, essentially a spinning disc with vanes, to fling gas outward at high velocity. That velocity gets converted into pressure through a diffuser. These are the machines that cool skyscrapers, data centers, university campuses. A single centrifugal chiller can produce 1,000 tons of cooling or more. That's the equivalent of melting about 12,000 tons of ice per day, which is a staggering amount of cooling from one machine. These are precision instruments. The impellers can spin at tens of thousands of revolutions per minute, and some modern designs use magnetic bearings, meaning the spinning shaft literally floats in a magnetic field, with no physical contact, no friction, no oil needed. It's almost science fiction, except it's sitting in the basement of buildings you walk into every day. But here's the thing that ties all of this compressor evolution together, and it's something that happened relatively recently that changed the game in a way that most people don't appreciate. It's the variable speed drive, sometimes called an inverter. For most of refrigeration history, compressors ran at one speed. They were either on or off. Your refrigerator would cool down to the set temperature, the thermostat would click, the compressor would shut off, the temperature would slowly drift up, the thermostat would click again, the compressor would start back up. On, off, all day and all night. And every time a compressor starts up, it draws a big surge of current, several times its normal running current, and it wears on the motor and the mechanical components. It's like driving a car by flooring the accelerator until you hit 60, then turning the engine off and coasting until you slow to 20, then flooring it again. It works, but it's not exactly efficient or gentle. A variable speed drive changes the frequency of the electrical power going to the motor, which changes the motor speed, which means the compressor can run fast when you need a lot of cooling and slow when you just need a little. Instead of cycling on and off, it just runs continuously, gently, matching its output to the actual cooling load moment by moment. The temperature stays more stable. The efficiency goes up dramatically. We're talking 20 to 40% energy savings in many applications, and the compressor lasts longer because it's not constantly hammering itself with start-stop cycles. This technology came largely from Japan. Companies like Toshiba and Daikin were pioneers in applying inverter technology to air conditioning in the 1980s. In Japan, where electricity is expensive and space is tight, the efficiency gains were compelling enough to drive rapid adoption. It took longer to catch on in the United States, where electricity was cheaper and the existing infrastructure was built around single-speed systems, but it's gotten there. Today, virtually all mini-split air conditioning systems use inverter-driven compressors, and the technology is increasingly standard in household refrigerators too. If you've noticed that modern refrigerators seem quieter than the ones you grew up with, this is a big part of why. The compressor isn't banging on and off anymore. It's just humming along at whatever speed it needs. And when you combine all of these threads, better compressors, better refrigerants, better controls, better insulation, you start to see something remarkable about the trajectory of refrigeration efficiency. A refrigerator today uses about a quarter of the energy that an equivalent refrigerator used in 1975. A quarter. That's not because of any single breakthrough. It's the accumulation of dozens of incremental improvements, each one shaving off a few percentage points of waste. Better door seals, more efficient fan motors, optimized condenser and evaporator coil designs, thicker insulation with better thermal resistance, smarter defrost cycles, variable speed compressors, and yes, better refrigerants with thermodynamic properties that are more closely matched to the operating conditions. This matters enormously because refrigeration and air conditioning together account for roughly 20% of all electricity consumed globally. 20%. That's a staggering number. Anything you can do to make these systems more efficient has a massive impact on total energy demand and, by extension, on carbon emissions. The efficiency standards that governments have imposed, the Energy Star program in the United States, similar programs in Europe and Asia, have been among the most effective energy policies ever implemented, precisely because they forced manufacturers to keep pushing on all of these incremental improvements simultaneously. But efficiency is only part of the modern refrigeration story. The other part, and this is something that's reshaping how engineers think about cooling in the 21st century, is the sheer scale of demand. Because here's what's happening right now, as you're lying here listening to this. The world is getting warmer, and as it gets warmer, more people need air conditioning. And as more people get air conditioning, the energy demand goes up, which in many parts of the world means burning more fossil fuels, which makes the world warmer, which means more people need air conditioning. It's a feedback loop, and the numbers are genuinely sobering. The International Energy Agency estimates that there are roughly 2 billion air conditioning units operating in the world right now. 2 billion. And by 2050, that number is expected to triple, to reach something like 5.5 billion units. Most of that growth is happening in countries that are both hot and rapidly developing. India, Indonesia, Brazil, Nigeria, the Philippines, parts of the Middle East. Places where rising incomes mean that hundreds of millions of people who have never had air conditioning are about to get it for the first time. And honestly, who could blame them? If you've ever spent a summer in Delhi, where temperatures can hit 45 degrees Celsius, you know that air conditioning isn't a luxury. It's a matter of survival. Heat kills more people globally than almost any other weather-related event. So the moral case for expanding access to cooling is overwhelming, but the energy math is daunting. Think about India alone for a moment. Right now, only about 10 to 15% of Indian households have air conditioning. In the United States, that number is over 90%. As India's economy grows and its middle class expands, air conditioning penetration is going to rise dramatically. Some projections suggest India could have over 1 billion air conditioning units by mid-century. 1 billion in one country. And India still generates a large share of its electricity from coal. So unless the energy grid decarbonizes at the same pace that air conditioning adoption accelerates, you end up in exactly that feedback loop, cooling the indoors while heating the outdoors. This is one of the defining engineering challenges of the 21st century. Not how to make cold. We figured that out a long time ago. But how to make cold sustainably, at planetary scale, for billions of people who need it. And engineers are attacking this problem from every angle you can imagine. Some of the approaches are refinements of technology we've already talked about. Variable speed compressors, better heat exchangers, smarter controls that learn your schedule and pre-cool your house during off-peak hours when electricity is cheaper and often cleaner. But some of the approaches are genuinely new, and a few of them are fascinating enough that they're worth spending a little time on. Let's start with one that sounds almost too simple to be real. District cooling. The idea is straightforward. Instead of every building having its own air conditioning system, you build one massive central cooling plant and pipe chilled water through insulated underground pipes to all the buildings in a neighborhood or a campus or even an entire city district. It's the same concept as district heating, which has been common in Scandinavian and Eastern European cities for over a century, just running in reverse. And the efficiency gains are significant because one large chiller plant can operate at much higher efficiency than hundreds of small individual units. You can use those big centrifugal compressors we talked about, the ones with magnetic bearings, running at their optimal speed, serving thousands of apartments and offices simultaneously. You also get economies of scale on maintenance, and you can integrate thermal storage, essentially making ice or chilling water at night when electricity demand is low, and using that stored cold during the peak afternoon hours. The most ambitious district cooling system in the world right now is probably in Dubai. Which makes sense, right? It's one of the hottest cities on Earth. Dubai has been building out district cooling infrastructure for years, and some estimates suggest that district cooling in Dubai uses about 40% less energy than equivalent conventional air conditioning would. That's an enormous saving in a city where cooling is the single largest category of electricity consumption. Other cities are following: Singapore, Hong Kong, parts of Paris. It's not a solution for everywhere, because the upfront infrastructure cost is huge and it works best in dense urban environments, but for the right setting, it's remarkably effective. Now here's one that's a bit more exotic: radiative cooling. This is the idea that you can cool objects by letting them radiate heat directly into outer space. And before you think that sounds like science fiction, it's actually based on well-understood physics. Everything that has a temperature emits thermal radiation. You, right now, lying there, are radiating infrared energy. The Earth's atmosphere is mostly opaque to infrared radiation. It absorbs and re-emits it, which is basically the greenhouse effect. But there's a window, a narrow band of infrared wavelengths, roughly between 8 and 13 micrometers, where the atmosphere is surprisingly transparent. Radiation at those wavelengths can pass straight through the atmosphere and escape into the cold of outer space, which has an effective temperature of about 3 Kelvin. Essentially absolute zero for practical purposes. So here's the clever part. In 2014, a team at Stanford led by Shanhui Fan and Aswath Raman created a multi-layer photonic film, incredibly thin, just a few micrometers, that was engineered to do two things simultaneously. First, it reflected nearly all incoming sunlight, so it didn't heat up from solar radiation. Second, it emitted thermal radiation very strongly in exactly that 8 to 13 micrometer atmospheric window. The result was that this material, sitting in direct sunlight on a rooftop in Palo Alto, California, cooled itself to nearly 5 degrees Celsius below the ambient air temperature, without using any energy at all. No compressor, no refrigerant, no electricity. Just a material that's been engineered to radiate heat into the void of space through a gap in the atmosphere's absorption spectrum. Now, 5 degrees below ambient doesn't sound like much, and at the moment, the technology is still in its early stages. You can't cool a building to a comfortable 22 degrees on a 40-degree day with radiative cooling alone. But as a supplementary system, something that pre-cools the fluid going into a conventional air conditioning system, reducing the work the compressor has to do, it could meaningfully reduce energy consumption. Several startups are working on scaling this up, turning that laboratory film into something you could manufacture in rolls and apply to rooftops like paint or adhesive sheeting. It's one of those ideas that might take a decade or two to become practical at scale, but the underlying physics is sound, and the potential is genuinely exciting. And then there are the approaches that go back to thermodynamics in ways that bypass the vapor compression cycle entirely. We've spent most of this journey talking about vapor compression because it dominates the world of refrigeration. Something like 90% of all cooling systems use it. But there are other ways to move heat. Thermoelectric cooling, for instance, uses the Peltier effect, discovered by Jean-Charles Athanase Peltier in 1834. When you pass an electric current through a junction of two different conducting materials, one side gets hot and the other gets cold. No moving parts, no refrigerant, just electrons carrying heat from one side to the other. You've probably encountered this in small portable coolers, the kind you plug into your car's cigarette lighter. They work, but they're not very efficient. Their coefficient of performance is much lower than a vapor compression system, so they've been limited to niche applications. But researchers are making progress on new thermoelectric materials, particularly bismuth telluride alloys, and more recently some promising work with tin selenide and organic-inorganic hybrids that could push the efficiency high enough to make thermoelectric cooling viable for larger applications. There's also magnetocaloric cooling, which exploits a property of certain materials, usually gadolinium alloys, that heat up when exposed to a magnetic field and cool down when the field is removed. You can build a cooling cycle around this effect, alternately magnetizing and demagnetizing the material while using water or another fluid to carry the heat away. No vapor, no high pressures, no greenhouse gas refrigerants. The Department of Energy in the United States has funded several research programs on magnetocaloric cooling, and there have been working prototypes. But the challenge is that the temperature change per cycle is small, typically only a few degrees, so you need to cascade many stages together to get useful cooling, and the cost of the magnetic materials and the powerful magnets required is still prohibitive for consumer products. But the fundamental thermodynamic efficiency can theoretically approach the Carnot limit more closely than vapor compression does, so the prize is worth chasing. And here's something that brings us full circle in a way that's almost poetic. Remember how we started this whole journey, way back at the beginning, talking about ice? About people cutting blocks of frozen lake water and storing them in insulated houses? Well, one of the most promising strategies for managing cooling demand in the 21st century is, in essence, a high-tech version of that same idea. Thermal energy storage. The concept is simple. You run your cooling equipment at night when electricity is cheap and often generated by cleaner sources, and you make ice, or you chill a tank of water, or you freeze a phase change material. Something like a specially formulated salt solution that melts and freezes at a useful temperature. Then during the day, when the building needs cooling and electricity prices are high, you circulate that stored cold through the building instead of running the compressor. Companies like Ice Energy and CalMac have been doing this for commercial buildings for years, and it works beautifully. You're essentially time-shifting your energy consumption, decoupling the moment you need the cold from the moment you make it. And this connects to something even bigger: the transformation of the electrical grid itself. As more and more electricity comes from solar and wind, which are intermittent by nature, the grid needs flexibility. It needs loads that can shift in time. And cooling systems, with their ability to store thermal energy, are perfect candidates for this kind of demand response. Your refrigerator could pre-cool itself a degree or two when the sun is shining and solar panels are flooding the grid with cheap electricity, then coast through the evening peak without drawing power. Your air conditioner could make ice at 2 a.m. when the wind is blowing and electricity is nearly free. Smart thermostats and grid-connected controls are already making this possible, and as the grid gets smarter and more renewable, this kind of flexibility becomes increasingly valuable. So what you're seeing, if you step back and look at the whole picture, is that refrigeration, this technology that started with a Boston ice merchant loading frozen blocks onto sailing ships, has become woven into the fabric of modern civilization in ways that touch almost everything: food safety, medicine, human comfort, industrial chemistry, data centers, which generate enormous amounts of heat and require massive cooling systems to keep servers from melting down. The global supply chain, which depends on an unbroken cold chain stretching from farms in Kenya to supermarkets in London. And now, the energy transition itself, where cooling systems are becoming both a challenge and a tool, a major source of electricity demand, and potentially a flexible resource that helps balance a renewable grid. And all of it, every bit of it, still comes back to the same basic thermodynamic principles that Sadi Carnot and Rudolf Clausius worked out in the 19th century. You're moving heat from a place where you don't want it to, a place where you don't mind it, and you're paying an energy cost to do it because the second law of thermodynamics says you must. That hasn't changed. What's changed is how cleverly, how efficiently, and at what extraordinary scale we've learned to do that work. And we keep finding new ways to do it better. Think about where we are right now tonight, in terms of the sheer ambition of what refrigeration engineers are attempting. There's a quiet revolution happening in the world of cooling that most people will never hear about. And it involves rethinking the entire relationship between buildings and the atmosphere. Not just cooling a room, but cooling it in a way that barely touches the electrical grid. We talked about Aswath Raman and Shanhui Fan's radiative cooling panels at Stanford, those remarkable surfaces that beam heat directly into outer space through the infrared window of the atmosphere. Well, that idea has kept growing. By the early 2020s, companies like Sky Cool Systems, which Raman co-founded, were installing rooftop panels on grocery stores and commercial buildings that use this principle to pre-cool the condenser fluid in conventional air conditioning systems. Here's the thing. They're not replacing the air conditioner entirely. They're making it work less hard. The panels cool the refrigerant fluid a few degrees before it enters the condenser, which means the compressor doesn't have to squeeze as hard, which means it uses less electricity. It's a beautifully practical application. You're essentially using the cold of outer space, which sits at about 3 Kelvin, just 3 degrees above absolute zero, as a free heat sink. And you're accessing it through a window in Earth's atmosphere that happens to be transparent to infrared radiation in the 8 to 13 micron wavelength band. The engineering challenge was designing a surface that radiates strongly in exactly that band while reflecting sunlight so it doesn't heat up during the day. That's what the multi-layer photonic structure achieves. And the energy savings are real. Somewhere around 10 to 20% reduction in cooling energy for the buildings where these systems have been deployed. Not world-changing on its own, but stack it with everything else we've been talking about. Variable speed compressors, smart grid integration, better refrigerants, thermal storage. And you start to see how the future of cooling is really about layering many clever ideas on top of each other. And then there's the food side, which honestly deserves a whole night of its own. The cold chain, that unbroken thread of refrigeration stretching from the moment food is harvested to the moment it lands on your plate, is one of the most consequential engineering systems in the world, and it's also one of the most uneven. In wealthy countries, the cold chain is robust. Nearly every step of the journey is temperature controlled. But in much of the developing world, the cold chain barely exists. The Food and Agriculture Organization of the United Nations has estimated that roughly 14% of the world's food is lost between harvest and retail. And in sub-Saharan Africa and South Asia, that number is significantly higher. A huge portion of that loss is due to lack of refrigeration. Fruits and vegetables rot in the heat before they can reach market. Milk spoils. Fish goes bad. Vaccines, and this is critical, lose their potency because they weren't kept cold during transport. The World Health Organization has estimated that nearly half of all vaccines in developing countries are wasted, in part because of cold chain failures. Think about what that means. A child doesn't get vaccinated not because the vaccine doesn't exist, but because no one could keep it cold enough on the journey from the distribution center to the rural clinic. So there's an enormous push right now to extend the cold chain into parts of the world that have never had it. And the engineering challenges are fascinating because you can't just ship a bunch of conventional refrigerators to a village that doesn't have reliable electricity. You need solutions that work off-grid or on intermittent solar power, or with minimal maintenance. One approach that's gained real traction is solar-powered vaccine refrigerators, units designed specifically for clinics in remote areas. Companies like Sundancer and SureChill have built refrigerators that can keep vaccines at the required 2 to 8 degrees Celsius range, even when the power goes out for days. The SureChill technology is particularly clever. It uses the unique property of water, the fact that water is densest at 4 degrees Celsius, not at 0. You remember we talked way back at the beginning about how heat behaves, how cold is really just the absence of heat. Well, here's a beautiful application of that principle. In a SureChill refrigerator, there's a compartment of water surrounding the vaccine storage area. When the solar panel is generating power during the day, the refrigeration system cools this water down to 0 degrees, and some of it freezes into ice at the top. But the liquid water at 4 degrees, being the densest, sinks to the bottom and surrounds the vaccines, keeping them at exactly the right temperature. When the power goes off at night or during cloudy days, the ice slowly melts and the 4-degree water continues to sink and circulate by natural convection, maintaining that precise temperature window without any electricity at all. No batteries needed, no backup generator. Just the physics of water density doing the work. It can hold temperature for days. And it's saving lives right now, today, in clinics across Africa and Southeast Asia. That's the kind of engineering that makes you feel good about the whole enterprise, isn't it? All those centuries of thermodynamic theory and mechanical tinkering and industrial development, and it comes down to keeping a vial of polio vaccine cold in a clinic in rural Ethiopia. Carnot would have appreciated the elegance of it, I think. Using the anomalous density of water, a quirk of hydrogen bonding that most people learn about in high school chemistry and then forget, to solve a life or death problem with 0 moving parts during the unpowered phase. But let's zoom out one more time, because I want you to hold the full picture in your mind as you drift off. The story of refrigeration is really a story about humanity's relationship with heat. For most of human history, we were at the mercy of temperature. Hot climates limited where we could live comfortably, what we could eat, how long food would last, what diseases would flourish. Cold climates had their own brutal constraints, but humans actually figured out heating pretty early. Fire is one of our oldest technologies. Cooling was the hard one. You can make heat easily. Making cold, as we've spent all this time exploring, requires you to fight the second law of thermodynamics. It requires ingenuity. It requires understanding what heat actually is at a molecular level, and then devising machines that can grab it and move it against its natural inclination to spread out and equilibrate. And we did it. Slowly, imperfectly, sometimes dangerously. Remember the early methyl chloride and sulfur dioxide refrigerators that occasionally killed people in their sleep when a seal leaked? But we did it. Frederic Tudor figured out that you could cut ice from a pond in Massachusetts and sell it in Calcutta. Jacob Perkins built a machine that could make ice from ether vapor in a London workshop in 1834. Carl von Linde engineered ammonia compressors reliable enough to transform the brewing industry. Willis Carrier figured out that you could control humidity and temperature together and make entire buildings comfortable. Thomas Migley gave us Freon, which seemed like a miracle until Sherwood Rowland and Mario Molina showed us it was eating the ozone layer. And then the whole world, every nation on Earth, agreed to stop using it in what remains one of the most successful environmental treaties in history. Now here we are, and the challenge has shifted again. The refrigerants are getting safer. The machines are getting more efficient. But the sheer scale of demand is growing so fast, especially as billions of people in hot climates gain access to air conditioning for the first time, that the energy implications are staggering. And yet, and this is what I find quietly hopeful, the engineering responses are extraordinary. Magnetic cooling that uses spinning magnets instead of compressors, elasticaloric cooling, which we haven't even talked about yet, materials like nickel-titanium shape memory alloys that absorb and release heat when you stretch and release them, with no refrigerant at all. Electrochemical cooling, where you use ion migration in liquid electrolytes to create temperature differences. These are all in various stages of research and development, and none of them are ready to replace your home air conditioner tomorrow, but they represent a broadening of the toolkit that's genuinely exciting. The vapor compression cycle has dominated for over a century, and it's been refined to remarkable efficiency, but it may not be the final answer. The thermodynamics doesn't care how you move the heat. Carnot's limit applies regardless of mechanism. What matters is getting as close to that theoretical maximum as possible while using materials that don't harm the atmosphere and energy that doesn't warm the planet. And maybe that's the most beautiful thread running through this whole story, the way each generation of engineers inherits the same fundamental physics but finds new ways to express it. The second law hasn't changed since Clausius formalized it in 1854. Entropy still increases in every isolated system. Heat still flows from hot to cold, unless you do work to reverse it. But the creativity humans have brought to working within those constraints, from Tudor's ice ships, to Linde's ammonia compressors, to Migley's chlorofluorocarbons, to scroll compressors, with variable speed inverter drives to photonic films that radiate heat into the void of space. That creativity is genuinely awe-inspiring when you lay it all out end to end. So tonight, wherever you are, the air around you is probably being conditioned in some way by a descendant of those early machines. Maybe it's a window unit humming softly. Maybe it's a central system you can't even hear. Maybe it's just the refrigerator in your kitchen, cycling on and off through the night, keeping tomorrow's breakfast cold. Inside that machine, a refrigerant is doing exactly what refrigerants have always done, evaporating, absorbing heat, getting compressed, releasing that heat somewhere else, condensing back to liquid, and starting the cycle again, over and over, all night long. A small, quiet act of thermodynamic defiance, repeated billions of times across the planet, in every home and hospital and server room and grocery store and vaccine clinic, moving heat from where it isn't wanted to, where it doesn't matter, paying the entropy tax, keeping things cool. It's a good thing to fall asleep to, I think. The idea that right now, all around the world, these little cycles are turning. Compressors are humming, refrigerant is flowing, heat is being moved. And somewhere, an engineer is working late, trying to figure out how to do it just a little bit better, a little more efficiently, a little more gently on the atmosphere, a little more accessibly for the people who need it most. That work goes on. It's been going on since Carnot sat down with his notebooks in Paris in the 1820s, and it'll keep going long after tonight. But for now, you don't need to think about any of it. The machines are running, the physics is holding, everything is exactly as cool as it needs to be, and you can just rest